Hello, and welcome to the last lab report for Physics 2212, Lab 5, Faraday's Law. In this report, I'll start with a brief introduction where I'll go over the purpose of this experiment, its results, and the physics concepts needed in order to understand the computational model. I'll then go into the experiment where I will talk about the procedure and what happened to the falling bar magnet. Following that, I will talk about the computational model I used to simulate a falling bar magnet through a tube of rings that have an induced electrical current in them from the falling magnet. Finally, I'll close with some closing comments by answering the what-if questions. The purpose of this experiment was to measure the time it took for the bar magnet to fall through a tube of aluminum foil. Then, I had to use Faraday's law and Lenz's law to explain the generation of an opposing force from the falling magnet slowing its descent. The results from the experiment can be seen below. The physics concepts needed in order to conduct this experiment were Faraday's law, which states that there is an induced current created and proportional to the rate of change of the flux through the surface, magnetic flux, which is the amount of magnetic field passing through an area, and Lenz's law, which states that the induced current created a magnetic field that opposes the change in flux. This creates an opposing magnetic force on the magnet, pulling it upwards. In the experiment, the falling bar magnet caused a downward change in flux through the rings as the magnetic force is increasing as the magnet gets further down the tube. Due to Lenz's law, this creates an induced force that points up, opposing the change in flux, slowing the magnet down. The induced current flows counterclockwise from above per the right-hand rule. The magnetic force can be found by multiplying the current by the cross product between delta L and B, which, since they're both pointing in the same direction, is just multiplied. Using the Savart law, the magnetic force is equal to the direction shown in the bottom. To the right is an image depicting what is going on in a singular ring in the tube. In reality, the aluminum tube is many rings stacked on top of each other, causing the magnetic force to observably make the magnet fall slower. The actual experiment consisted of measuring my tube of aluminum foil for the computational model, and then timing the time it took for the magnet to fall through the tube 5 times and averaging it. The poles of the tube were found using the same app from the third lab that calculated the magnetic moment of a bar magnet, magnetometer. This experiment found that on average it took 1.12 seconds for the magnet to fall through this 0.3 meter tube. This slide shows my measured values that will be needed for the computational model. The resistivity of the foil was given to us in the starter code, and the magnetic moment of the bar magnet was found in the third experiment that I mentioned before, which was 2.4 amp-meters squared. The direction of the magnetic moment is shown to the left, pointing out of the North Pole. The experimental procedure asks what happened to the falling magnet and how does that compare to if the magnet was dropped outside of the tube. Due to the cylinder applying an upward force on the falling magnet according to Lenz's law, the magnet starts to float once dropped, causing it to fall slower than normal. The average time it took for the magnet to fall was 1.12 seconds. Here are parts of my code that I used. The top left 2 blocks show my measurements of the aluminum tube as well as the mass and magnetic moment of the bar magnet. The top right block shows how the magnetic field was calculated using the Savart law, which gives an equation for the magnetic field from the magnetic moment of the bar magnet. Below that is a calculation of the change in flux over time from each ring in the tube. This is then thrown into a while loop for the time that the magnet is in the tube that updates the position of the magnet using the force of gravity and the magnetic force from the induced current in the rings according to Faraday's law and Newton's second law. This while loop is what determines the time it takes for the magnet to fall through the tube. Here's the computational model. The left shows the magnet at the top of the tube, and you can see the magnetic force opposing the force of gravity to the right. The graph shows the position and velocity of the magnet versus time. The velocity is a decreasing negative slope until the very end, when part of the magnet is outside the tube, causing the magnetic force to decrease, thus increasing the downward velocity of the magnet. The model predicted the magnet would fall out of the tube in 0.512 seconds. Finally, the first what-if question asked, what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? Well, since the current and resistance are inversely proportional, having little to no resistance would cause the magnetic force to grow, thus slowing the fall of the magnet more. The second what-if question asked, what if holes or slots were cut into the tube? How would this affect the current in the model? Well, when there are holes in the tube, there would be less full rings for the magnet to impose an electric current in, thus creating less rings to impose an opposite force on the falling magnet. This would cause the magnet to fall faster. And that is all. Thank you for listening.